Three aircraft define Boeing's future. The 737 MAX dominates narrow-body markets with thousands of orders. The 787 Dreamliner revolutionized long-haul efficiency and changed how airlines fly. The 777X represents the next generation of wide-body giants with technology never seen before. But how does Boeing actually build these machines? From composite wings to final assembly, each aircraft demands precision at massive scale. Today we are taking you inside Boeing's factories to see exactly how the company manufactures its three best-selling jets. From the 777X to the Dreamliner to the MAX, here is how Boeing builds the future of aviation.
It was an unprecedented display of demand for a new airplane. Leaders of some of the world's top airlines announced at the Dubai Air Show a record-breaking number of orders and commitments for Boeing's newest jet, the 777X.
The Boeing 777X represents one of the largest and most advanced commercial aircraft ever built. This aircraft is not simply another wide-body jet. It is the evolution of the iconic 777 family, designed to carry more passengers farther while consuming significantly less fuel than previous generations. The program consists of two main variants. The 777-9 offers high capacity, seating approximately 426 passengers in typical two-class configurations. The 777-8 provides ultra-long range, capable of flying roughly 8,745 nautical miles non-stop. Together, these variants position the 777X as Boeing's answer to modern long-haul efficiency and direct competition with Airbus. The scale of this program is staggering. Boeing invested tens of billions of dollars developing the 777X. The aircraft incorporates revolutionary technologies never before used in commercial aviation. From composite wings to folding wingtips to the most powerful engines ever built, the 777X pushes engineering boundaries across every system. Understanding how this giant is built requires examining the entire manufacturing process from raw materials to final assembly. The most revolutionary feature of the 777X is its massive composite wings. These are the largest wings ever built for a commercial aircraft. The wingspan measures 71.8 meters in flight, longer than the entire fuselage of many narrow-body aircraft. These wings are manufactured using carbon fiber composites rather than traditional aluminum. Carbon fiber offers exceptional strength while weighing significantly less than metal. This weight reduction translates directly into fuel savings and increased payload capacity. Manufacturing these enormous composite wings requires specialized facilities with advanced automation. Boeing built dedicated wing manufacturing centers specifically for the 777X program. These facilities house some of the most sophisticated production equipment in aerospace manufacturing. Robotic systems play critical roles throughout wing construction. Automated fiber placement machines lay down carbon fiber material in precise patterns. These robots can position material with tolerances measured in fractions of millimeters. Human workers could never achieve this level of consistency across such large structures. The carbon fiber material arrives in large rolls. Robots precisely cut and lay the material in multiple layers. Each layer is oriented at specific angles to provide strength in different directions. The layup process creates the basic wing structure. Once layup is complete, the wing sections enter massive autoclaves. These are essentially giant ovens that cure the composite material under high temperature and pressure. The autoclave process bonds all the layers together into a single unified structure. Precision drilling techniques are used to create thousands of holes for fasteners and system installations. Automated drilling machines ensure every hole is positioned exactly where engineering specifications require. Even slight misalignment could create structural weaknesses. Wing assembly involves joining multiple large sections together. The center wing box, outer wing panels, and various substructures must align perfectly. Laser measurement systems verify positioning throughout the assembly process. Advanced automation extends beyond just the wings. Fuselage sections also utilize robotic assembly techniques. Automated riveting machines install thousands of fasteners. Robots apply sealants and coatings. The manufacturing process is becoming increasingly automated and digital. Boeing uses digital twin technology throughout 777X production. Every aircraft has a complete digital model that updates in real time as manufacturing progresses. Engineers can identify and resolve issues virtually before they affect physical production. The folding wingtips represent one of the 777X's most distinctive innovations. These wingtips solve a critical problem that would otherwise limit the aircraft's efficiency. The 777X wings are so large that they exceed the 65-meter span limit for airport gate compatibility. Most airports worldwide are designed around this gate limit. Aircraft with larger wingspans cannot access standard gates without expensive airport infrastructure modifications. Boeing's solution was brilliant. Design wings for optimal aerodynamic efficiency in flight, then make the tips fold upward on the ground to reduce the span to 64.8 meters. Each wingtip measures approximately 3.5 meters. When the aircraft lands and taxis to the gate, the tips fold upward. This happens through a simple mechanical system. No hydraulic power is required. The folding mechanism is designed for reliability and ease of maintenance. Safety was paramount in wingtip design. Multiple redundant locking mechanisms ensure the tips cannot accidentally fold during flight. Visual indicators on the flight deck confirm wingtip position. Ground crews can also visually verify the tips are properly extended before takeoff. The folding wingtips enable the 777X to maintain its enormous wingspan for aerodynamic efficiency while still operating at standard airport gates. This eliminates the need for costly airport modifications that would otherwise be required. The GE9X engines are among the most powerful jet engines ever built. Each engine produces over 110,000 pounds of thrust. This massive power is necessary to propel the 777X's substantial weight and large wingspan. But power alone does not make these engines revolutionary. The GE9X incorporates advanced materials and design innovations that significantly improve fuel efficiency and performance compared to previous generation engines. The fan diameter measures 134 inches, making it larger than the fuselage of a Boeing 737. This enormous fan moves massive amounts of air. The larger bypass ratio, the proportion of air flowing around the engine core versus through it, improves efficiency dramatically. Advanced composite materials are used extensively throughout the engine. Carbon fiber composites in the fan blades and fan case reduce weight substantially. Ceramic matrix composites in the hot sections withstand extreme temperatures while weighing less than metal alternatives. The combustor uses advanced cooling and fuel injection technology. This enables higher operating temperatures, which improves thermodynamic efficiency. The result is approximately 10% better fuel efficiency compared to the GE90 engines powering the current 777 fleet. Manufacturing these massive engines requires specialized facilities. GE operates dedicated production lines for GE9X assembly. Each engine contains thousands of precisely manufactured components. Assembly and testing take weeks per engine. Every engine undergoes extensive ground testing before installation on an aircraft. Test cells subject engines to extreme conditions, simulating various flight scenarios. Engineers verify performance, durability, and safety across the operational envelope. Final assembly of the 777X occurs at Boeing's Everett facility in Washington State. This factory is the largest building by volume in the world. The facility was originally built for Boeing 747 production but now houses assembly lines for multiple wide-body programs. The 777X assembly process begins with major fuselage sections arriving at the factory. Spirit Aerosystems manufactures forward fuselage sections. Other suppliers provide mid and aft fuselage sections. These massive cylindrical structures travel to Everett by various transportation methods. The assembly line uses a moving production system. Aircraft progress through multiple stations as work is completed. This flow production approach improves efficiency compared to building aircraft in fixed positions. At early stations, fuselage sections are joined together. Precision alignment is critical. Laser measurement systems ensure sections mate perfectly. Even small misalignments would create structural issues and aerodynamic problems. Systems installation happens progressively as the fuselage moves down the line. Electrical wiring, hydraulic lines, environmental control ducting, and countless other systems are installed and connected. Thousands of workers contribute specialized skills at different stations. The wings arrive from the composite manufacturing facility as complete assemblies. Attaching these enormous structures to the fuselage represents one of the most critical assembly steps. Automated positioning systems help align the wings precisely. Landing gear installation requires careful coordination. These massive structures must support the aircraft's entire weight during ground operations. Proper alignment and attachment are essential for safety. The engines arrive from GE's facilities and are mounted to the wings. Each engine weighs several tons and requires specialized lifting equipment for installation. Connections for fuel, hydraulics, electrical systems, and control linkages must all be completed properly. Interior installation occurs in later assembly stations. Floor panels, sidewall panels, overhead bins, seats, galleys, and lavatories are all installed. The cabin is transformed from an empty shell into a passenger-ready environment. Once physical assembly is complete, extensive system integration testing begins. Every system on the aircraft must be verified individually and then tested in combination with other systems. Electrical systems are powered up and tested. Hydraulic systems are pressurized and checked for leaks in proper operation. Flight control surfaces are moved through their full range of motion. Environmental control systems are activated. Avionics systems are booted and tested. This systems testing identifies any installation errors or component failures before first flight. Correcting problems on the ground is far easier and safer than discovering them in flight. Ground testing includes engine runs. The aircraft is securely restrained while engines are started and operated at various power settings. Engineers verify proper engine operation, fuel system performance, and integration with aircraft systems. Taxi testing comes next. The aircraft is towed to the runway and pilots conduct high-speed taxi tests. These verify ground handling characteristics, braking systems, and nose-wheel steering. Speeds approach takeoff velocity, but the aircraft does not become airborne. First flight represents a critical milestone. Test pilots take the aircraft airborne for the first time. The initial flight typically lasts several hours and tests basic flight characteristics. Engineers monitor hundreds of parameters in real time. Additional flight testing follows over many months. Test aircraft fly hundreds of hours, evaluating performance across the entire operational envelope. Extreme conditions are simulated. Systems are tested to their limits. Every aspect of aircraft operation is validated. The Federal Aviation Administration maintains close oversight throughout testing. Regulators observe tests and review data. Certification requires demonstrating that the aircraft meets all safety and performance requirements. The 777X represents the future of long-haul aviation. It combines cutting-edge materials, manufacturing automation, and aerodynamic innovation into one of the most complex machines ever built. The composite wings reduce weight while improving aerodynamic efficiency. The folding wingtips enable operation at standard airports despite the massive wingspan. The GE9X engines deliver unprecedented power and efficiency. Advanced avionics and systems provide enhanced capabilities. For airlines, the 777X offers compelling economics. Better fuel efficiency reduces operating costs substantially. Higher capacity enables more revenue per flight. Longer range opens new nonstop route possibilities. The aircraft addresses airline needs for the next several decades. For passengers, the 777X provides enhanced comfort. Larger windows flood the cabin with natural light. Higher cabin humidity and lower cabin altitude reduce fatigue. Modern interior designs improve the travel experience. For Boeing, the 777X represents validation of their long-term wide-body strategy. Boeing set ambitious goals. The 787 had to be significantly more efficient to operate. It needed to offer substantially lower cost per seat for airlines. Boeing designed the 787 to achieve approximately 20% better efficiency than the 767 it would replace. The company also recognized growing attention airlines, governments, and passengers were paying to aviation's environmental impact. Sustainability became a major design driver alongside economics. The main design changes that contributed to efficiency improvements included revolutionary composite fuselage construction. The 787 became the first major commercial aircraft using carbon fiber composite components extensively in fuselage and wing construction. This approach makes the aircraft considerably lighter while still offering exceptional strength. The weight reduction translates directly into fuel savings. Every pound saved means less fuel burned over millions of flight miles. Aerodynamic improvements included distinctive raked wingtips. These reduce wing vortex drag in similar ways to traditional winglets, but with even better performance. Every aerodynamic refinement compounds efficiency gains. New, dramatically more efficient engines provided additional advantages. The 787 can take either the General Electric GNX or the Rolls-Royce Trent 1000 engine. Both represent generational leaps in powerplant technology. Boeing launched the project initially known as 7 Echo 7 in January 2003. The letter E stood explicitly for efficiency. By July 2003, the Dreamliner branding was firmly in place. The first customer order came from Japanese airline All Nippon Airways in April 2004. Aircraft development represents an enormously expensive undertaking. This is especially true for clean sheet designs like the 787. Total development costs were estimated at over $32 billion. That staggering figure reflects the technical challenges and risks involved. The 787 first flew in 2009, delayed significantly from the original 2007 target. It finally entered commercial service in October 2011 with All Nippon Airways. Boeing also embarked on an ambitious global marketing campaign. Starting in December 2011, Boeing launched a 6-month Dream Tour. The aircraft visited locations across Europe, Africa, China, Thailand, the Middle East, and the United States. The tour generated tremendous publicity and customer interest. The 787 and Airbus's response with the A350 provide excellent examples of how the two manufacturers compete and learn from each other constantly. In many ways, Boeing's decision to develop the 787 was remarkably bold. A clean sheet design with such aggressive efficiency focus represented a costly gamble. The market for this type of aircraft was not yet proven when Boeing committed. At the time, Airbus was focusing heavily on larger capacity aircraft with the massive A380. Boeing still had the 747 competing in this segment. Ultimately, the A380 gave Airbus leadership in sheer capacity. However, smaller and more efficient quickly proved to be where the industry would actually head. Boeing's bet paid off dramatically. Prior to the 787's launch and subsequent success, Airbus had been planning a new mid-capacity widebody based on the A330. This would feature new engines and partial carbon fiber construction. Otherwise, it would share extensively with its predecessor. The European manufacturer announced a revised clean sheet A350XWB at the 2006 Farnborough Air Show. This late decision meant the A350XWB did not enter service until 2015 with Qatar Airways. That came 4 years after the 787 entered service. Both Boeing and Airbus frequently construct aircraft in multiple locations with centralized production lines for final assembly. Airbus was actually conceived around this distributed concept. Several smaller European manufacturers came together in 1970 to challenge larger United States competition. Starting with the Airbus A300, components have always been constructed at various locations around Europe. Boeing historically focused production more tightly in the United States. Production facilities exist at Renton and Everett in Washington. Later, North Charleston in South Carolina was added. The 787 was originally assembled at Everett alongside all other Boeing widebodies. In 2011, a second assembly line was established at North Charleston to handle increased production rates. The 787-10 variant is produced exclusively in North Charleston. Boeing is currently consolidating all 787 production at this single location. Boeing dramatically increased outsourcing and third-party construction for the 787 program. Although all final assembly occurs in the United States, many critical components are constructed elsewhere by other companies. This global supply chain includes major components from around the world. The main wings and central wing box come from Mitsubishi Heavy Industries in Japan. Wing trailing edges are built by Kawasaki Heavy Industries, also in Japan. Wing tips are manufactured by Korean Air in South Korea. The tail and horizontal stabilizer along with central fuselage sections are constructed by Alenia Aeronautica in Italy. Forward fuselage sections come from Spirit Aerosystems in the United States and Kawasaki Heavy Industries in Japan. Main landing gear is produced by a combination of Kawasaki Heavy Industries in Japan and Messier Bugatti Dowdy in the United Kingdom. Passenger doors are built by Latecoère in France. Cargo doors come from Saab in Sweden. Finally, the aft fuselage section and tail fin are handled by Boeing directly. Boeing operates 4 large fuselage transporters known as Dreamlifters. These remarkable aircraft were developed from the 747-400 platform. They feature lengthened expanded fuselages specifically to carry aircraft components. The Dreamlifter was introduced specifically for 787 assembly. It efficiently brings together components from Japan, Italy, France, and the United Kingdom to factories in South Carolina and Washington. The Dreamlifter can carry separate fuselage sections and wings for most 787 variants. However, it is not large enough for the 787-10 mid-fuselage section. After that section is assembled from smaller components in North Charleston, it cannot be flown to Everett. This logistical constraint is one reason why all 787-10 production occurs in North Charleston. In October 2020, Boeing announced consolidation of all 787 production to its North Charleston facility beginning in 2021. This decision followed reduced demand and slowed production during the pandemic. It seems likely production will remain concentrated there for the foreseeable future. The last 787 at Everett was completed in February 2021. As mentioned earlier, the 787 focuses intensely on efficiency. This is clearly visible in the total redesign of the airframe. It became the first commercial aircraft relying heavily on composite materials rather than traditional aluminum alloys. Approximately 50% of materials used are carbon fiber, reinforced plastic, and other advanced composites. Only 20% is aluminum. Another 15% is titanium, which is also metal but proven to require lower maintenance. Overall, this material selection gives the 787 a 20% weight reduction compared to conventional construction, according to Boeing. It also reduces required maintenance on the fuselage due to fatigue and corrosion issues that plague aluminum aircraft. The composite fuselage had profound influence on 787 construction methods. Composite structures can be molded into virtually any shape. This allowed separate entire fuselage barrel sections to be manufactured in different locations. Traditional aluminum construction requires sheets to be bolted together painstakingly. Composite barrels eliminate this labor-intensive process. You can see this carbon fiber construction in action if you watch the wings as the 787 takes off. The more flexible wings bend upward noticeably and remain this way throughout flight. This flexing is more efficient with reduced drag and improved overall performance. Moving forward with consolidated production in North Charleston, South Carolina, components are either built at that location or transported there for assembly. Within the North Charleston facility, separate factories handle subassembly of different fuselage sections. These include the mid-body sections combining parts from Italy and Japan. Aft body sections handle the final portion of the fuselage and tail section. In these facilities, separate sections are joined together carefully. Necessary wiring, ducts, hydraulics, and other equipment are also added to fuselage sections at this stage. This pre-integration simplifies final assembly significantly. Previously, fuselage sections for the 787-8 and 787-9 from these facilities would be transported to Everett for final assembly. That changed with production consolidation. A further facility known as the Interiors Responsibility Center assembles many necessary interior equipment items. This includes floor and ceiling panels, storage bins, and crew rest facilities. Pre-assembling these components streamlines installation during final assembly. One main building houses the final assembly line. This enormous facility can handle up to 8 787 aircraft simultaneously at different assembly stages. It brings together previously sub-assembled fuselage sections with wings and tail components. Watching these massive sections come together is genuinely impressive. Production at the North Charleston final assembly line completed 14 aircraft per month in 2019. This represented peak production rates. The pace slowed significantly in 2020 and 2021 due to the pandemic and several quality control issues. By the end of 2020, production had fallen to just 5 aircraft per month. This dramatic reduction reflected both demand collapse and necessary quality improvements. Several separate issues were identified and investigated by the FAA during this period. Problems included joining material known as shims used to fill gaps where fuselage parts were mated. Some gaps were wider than allowable specifications. Additional issues emerged with the horizontal stabilizer. Most recently, problems appeared with decompression panels separating the cargo area from the passenger area. These issues led to aircraft groundings and extensive inspections. They also triggered comprehensive reviews of the assembly line and quality control processes. In March 2021, the first 787 since October 2020 was finally handed over to a customer. This marked an important milestone in resolving quality problems. By late April, inventory backlog stood at around 100 completed aircraft awaiting delivery. With issues resolved, Boeing hoped to deliver these by the end of 2021. As of March 2026, Boeing has successfully worked through these challenges. Production has stabilized at sustainable rates. Quality control processes have been strengthened considerably. The lessons learned during this difficult period improved manufacturing processes significantly. The 787 has proved tremendously popular with airlines worldwide. Its point-to-point capabilities and efficient operation enable routes previously impossible to serve profitably. Airlines can fly directly between smaller cities on intercontinental routes. This operational flexibility transformed airline network planning. Rather than funneling all traffic through major hubs, airlines can serve passenger demand more directly. The 787 made this economic reality possible. However, the aircraft has not been without substantial challenges. Production issues have been a significant part of this story. Manufacturing complexity creates ongoing risks that Boeing must manage carefully. Looking forward, the 787 program appears healthy. Demand remains strong. Airlines continue ordering Dreamliners for fleet modernization and expansion. Boeing aims to increase production gradually as supply chains stabilize. The fundamental efficiency advantages that made the 787 successful remain valid. Airlines need fuel-efficient wide-body aircraft. The 787 delivers this better than alternatives in many applications. Production processes continue evolving. Boeing learns from experience and implements improvements. The North Charleston facility benefits from consolidated operations and focused expertise. The 787 program represents a watershed moment in aviation manufacturing. Composite construction became standard for new aircraft. Global supply chains proved viable despite complexity. Twin-engine widebodies replaced four-engine giants. From start to finish, building a 787 requires extraordinary coordination across continents. Suppliers in Japan, Italy, France, Korea, Sweden, and the United States all contribute critical components. The Dreamlifter aircraft shuttle parts across oceans. Finally, everything comes together in South Carolina. This distributed manufacturing model reflects modern aerospace industry reality. The Boeing 737 is the best-selling commercial jetliner in history. More than 490 operators worldwide fly this iconic aircraft. One 737 takes off or lands somewhere every 1.5 seconds. There are approximately 2,873 in the air at any given moment. The 737 family has carried more than 22 billion passengers since the program launched in the mid-1960s. This represents an extraordinary achievement in commercial aviation history. Boeing's Renton facility stands as the world's most productive airplane factory. As of March 2026, the plant is working toward producing approximately 42 Boeing 737 MAX aircraft per month. This represents the fastest-selling airplane in Boeing's history. The production process is remarkably efficient. It takes just 9 days for a plane to complete the assembly loop. Let's break down exactly how Boeing transforms raw fuselage sections into completed aircraft. The journey begins before the fuselage even arrives at Renton. Spirit Aerosystems in Wichita, Kansas manufactures the main fuselage sections. These hollow cylindrical shells travel by rail to the Seattle area. You may have seen these distinctive green fuselages being transported by train. They arrive as essentially empty shells coated in protective green primer. Boeing washes this coating off when the paint process begins later. When fuselages arrive at the Renton facility, they enter the massive factory building. Yellow overhead cranes dominate the production area. These powerful cranes lift and position fuselage sections with precision. The first 3 days focus entirely on what Boeing calls systems installation. This is where the airplane gets its guts. Workers install extensive electrical systems throughout the fuselage. Ventilation ducting routes air through the structure. Paneling begins covering interior surfaces. This phase resembles building a house. Engineers install the plumbing and electrics first. Insulation goes in. The internal infrastructure takes shape before exterior components attach. Hundreds of workers swarm over each fuselage during these initial days. They follow detailed engineering drawings. Every wire, tube, and duct must be positioned exactly. Quality inspectors verify each installation step. The work happens in specialized bays designed for this system's installation phase. Fuselages remain stationary while teams complete this critical work. Precision matters enormously because correcting mistakes later becomes exponentially more difficult. On the 4th day, the transformation becomes dramatic. The overhead cranes return. They carefully lift the fuselage and reposition it to a station called wing-to-body join. This is where the aircraft finally starts looking like an airplane. The wings arrive separately from Boeing's fabrication facilities. These massive structures contain fuel tanks, flight control surfaces, and mounting points for engines. Attaching wings requires extraordinary precision. Workers use laser guidance systems to align wings perfectly with the fuselage. Tolerances measure in fractions of millimeters. Even slight misalignment would affect flight characteristics and structural integrity. The vertical fin, commonly called the tail, gets installed during this phase. The landing gear attaches to reinforced mounting points in the fuselage and wings. Suddenly, the aircraft can support its own weight. This represents a critical milestone. What arrived as a hollow tube has become recognizably an aircraft. The basic airframe is complete. Day 5 brings the installation of the horizontal stabilizer. This component mounts at the rear fuselage. It provides pitch control during flight. Precise alignment with the vertical fin is essential. Functional testing begins during this phase. Engineers start verifying that installed systems work correctly. Wiring gets tested for continuity and proper connections. Flight control linkages are checked for smooth operation. Workers begin building out the interior. Floorboards go down throughout the cabin. Galleys start taking shape. Lavatories begin installation. The aircraft's passenger-carrying mission becomes visible. This phase also involves finishing internal floor structures. Cargo areas receive appropriate fittings and tie-down points. The aircraft is being prepared for its operational life carrying passengers and freight. Day 6 represents when the plane truly comes alive. Engineers apply electrical power to the aircraft for the first time. That flashing red beacon light activates. There's power flowing through the airplane's electrical systems. Large-scale systems testing now becomes possible. Does the landing gear retract properly when commanded? Do flight control surfaces move correctly? Are hydraulic systems functioning as designed? This testing is critical. The landing gear will retract the next time during the aircraft's first flight. It absolutely must work perfectly. Engineers verify every aspect of the retraction and extension system. Environmental control systems get tested. Pressurization equipment is verified. Backup systems are checked. Redundancy is fundamental to aircraft safety. Every system requires thorough validation. On day 7, the aircraft's weight settles onto its own wheels. The jacks supporting the aircraft during assembly are removed. The plane stands on its landing gear for the first time. The engines arrive and get mounted to the wings. For the Boeing 737 MAX family, these are CFM International LEAP 1B engines. The MAX features a 69-inch fan diameter. These engines are significantly larger and more efficient than previous generation power plants. Engine installation involves connecting extensive networks of wires, cables, and fuel lines. Hydraulic systems connect. Engine control systems integrate with the flight deck. Fire suppression systems are installed and tested. The engines represent the most expensive components on the aircraft. Handling requires extreme care. Specialized equipment positions engines precisely under the wings. Workers then secure them to mounting pylons. Day 8 focuses on critical testing of flight control surfaces. Flaps extend and retract. Ailerons move through their full range. Rudder and elevator systems are verified. Spoilers deploy correctly. All these parts have been checked in isolation during earlier phases. Now it's crucial they work together as an integrated system. The flight control computers must correctly command every surface. The cockpit undergoes comprehensive testing. The Boeing 737 MAX features advanced displays derived from Boeing 787 technology. High-resolution screens provide pilots with extensive information. These systems must function flawlessly. Pilots will rely on these instruments during every phase of flight. From takeoff to landing, the flight deck must provide accurate, timely information. Testing verifies every display, switch, and control operates correctly. As of March 2026, the Boeing 737 MAX family includes 4 variants. The MAX 7 is the smallest, serving markets requiring lower capacity. The MAX 8 has become the workhorse variant with balanced capacity and range. The MAX 9 offers increased seating. The MAX 10 provides maximum capacity within the Boeing 737 platform. Each variant shares common systems and flight deck design. This commonality allows pilots to transition between variants easily. Airlines value this flexibility enormously. The MAX incorporates several distinctive features. Advanced technology winglets with split scimitar design reduce drag significantly. The APU features a redesigned tail cone. Boeing eliminated vortex generators on the aft tail. The nose landing gear sits 20 centimeters higher than previous 737 generations. Inside, all MAX aircraft feature Boeing Sky interior. This modern cabin design provides larger overhead bins, improved lighting, and better passenger comfort. Airlines strongly prefer this interior configuration. The 9th day brings customer inspection. Airline representatives walk through their aircraft thoroughly. They verify specifications match the purchase agreement. They check interior configurations, equipment installations, and overall quality. This customer acceptance inspection is critical. Airlines are making massive investments. They want assurance the aircraft meets all requirements. Boeing representatives accompany customers, addressing any questions or concerns. Once the customer approves, the aircraft is ready for factory rollout. It gets towed out of the massive Renton production building. This moment represents completion of the assembly phase, but the aircraft is not yet ready for passenger service. It moves to Boeing Field, also known as King County International Airport. This facility sits adjacent to the Renton plant. At Boeing Field, ground testing intensifies. Engineers run the engines extensively. Taxi tests verify ground handling characteristics. Systems operate under realistic conditions for the first time. Then comes first flight. Test pilots take the aircraft airborne. They verify flight characteristics match predictions. All systems are evaluated during actual flight operations. This flight testing typically lasts several hours. After successful first flight and additional testing, the aircraft returns for final preparations. It enters the paint facility. Boeing washes off the protective green primer coating. The aircraft receives the customer's livery and markings. Final interior completion happens after painting. Seats are installed. Cabin furnishings are fitted. Entertainment systems are activated if specified by the customer. The aircraft transforms into its final customer-ready configuration. Throughout this entire process, quality control is relentless. Inspectors verify every step. Documentation tracks every component installed. Any deviation from specifications gets flagged immediately. As of March 2026, Boeing continues refining the production process. The company works closely with the FAA under heightened oversight. Quality improvements implemented after recent challenges have strengthened the manufacturing system. Production rates have gradually increased. Boeing received FAA approval to produce up to 42 aircraft per month. Plans call for eventual increases to 47 per month by mid-2026. Further increases to 52 and 57 monthly units are scheduled for subsequent years. These production increases depend entirely on maintaining consistent quality. The FAA will not permit higher rates if quality metrics decline. Boeing must demonstrate sustained excellence before regulators approve further ramp-ups. The Boeing 737 MAX has proven remarkably popular despite earlier challenges. As of March 2026, Boeing has secured over 4,500 MAX orders globally. This demonstrates airlines' confidence in the aircraft's capabilities and economics. The MAX 8 variant dominates orders. It went first to Malindo Air in Malaysia. The MAX 9 followed, with Lion Air taking initial deliveries. The MAX 7 completed flight testing and entered service with Southwest Airlines. The MAX 10 is approaching certification with service entry expected in 2026. Many industry observers believe the MAX 10 will effectively replace the Boeing 757 in airline fleets. The MAX 10 offers similar capacity with modern efficiency. It fits existing airport gates and infrastructure. Airlines value this compatibility highly. The Boeing 737 MAX is remarkably versatile. Airlines deploy it on 30-minute regional flights. Other carriers use it for routes approaching 7 hours. This flexibility makes the aircraft attractive across diverse markets. Fuel efficiency represents the MAX's most compelling advantage. The Leap 1B engines deliver approximately 14 to 20% better fuel consumption than previous generation 737 aircraft. For airlines, this translates directly to lower operating costs and improved profitability. The advanced winglets contribute additional efficiency gains. Improved aerodynamics reduce drag throughout the flight envelope. These incremental improvements compound into substantial fuel savings over millions of flight hours. Boeing's Renton facility represents industrial efficiency at its finest. The production line operates with precision timing. Every station has specific tasks. Aircraft move through the system in carefully orchestrated sequence. Thousands of workers contribute to each aircraft. Engineers, technicians, inspectors, and specialists all play critical roles. Their coordinated efforts transform components into complete aircraft in just 9 days. This 9-day cycle represents active assembly time. Component manufacturing, supplier coordination, and pre-delivery testing add additional time. But the core assembly process at Renton completes remarkably quickly. The Boeing 737 MAX stands as testament to continuous improvement. The basic design dates to the 1960s, yet Boeing keeps modernizing and refining the platform. New engines, advanced materials, and improved systems keep the Boeing 737 competitive. From an empty fuselage shell arriving by rail to a completed aircraft ready for first flight, the transformation takes just 9 days. This remarkable achievement demonstrates Boeing's manufacturing expertise and the Boeing 737 program's enduring success. As March 2026 arrives, the Boeing 737 MAX production line continues operating efficiently. Quality metrics are improving. Delivery rates are increasing. Airlines worldwide continue ordering these aircraft for fleet renewal and expansion. The 9-day journey from start to finish represents one of commercial aviation's most impressive manufacturing achievements. The Boeing 737 MAX emerges from this process ready to serve airlines and passengers for decades to come.